This is part 3, the study guide for the chemistry final exam. We need to finish up one last concept on chapter 6, or is this chapter 6? Chapter 4, actually. And then we'll be getting to this material right here for chapter 9, and we'll be doing about a page and a half of this for today. And we'll conclude the study guide on the following day. So, difference between atoms, isotopes, and ions. At any time, if you need to pause, I'm going too fast, you're welcome to do so. So, atoms. Atoms are, by definition, they are neutral, meaning they don't have any charge. So, meaning the positives and the negatives in the atom have to be the same, which means that the number of protons are going to have to equal the number of electrons. Isotopes, if you remember from the previous page, isotopes have the same number of protons and they have a different number of neutrons. Isotopes are an atom that's very, very similar in that they have the same number of protons. So hydrogen 1 and hydrogen 2, they both have 1 proton, but hydrogen 1 has 0 neutrons, hydrogen 2 has 1 neutron. So they have different number of neutrons, so therefore they have different masses, but they're considered to be the same element because they have the same number of protons. Ions have a difference in charge, so these are going to be charged atoms. So the number of protons does not equal the number of electrons. So it does not equal the number of electrons. So we're either losing or we're gaining our electrons. If you lose an electron, you're losing a negative, you become a positive ion. If you gain a negative electron, you're going to become a negative ion. So that's the conclusion of the prior chapter. Going on to chapter 9, this is a lot of naming things. No difference between monoatomic and polyatomic ions. So mono means one, poly means many. So an example of a monoatomic ion could be something like chlorine, with a chloride ion. You can also have the aluminum ion, such as this. So monoatomic doesn't mean that their charge is going to be 1. It means that they are a single atom with a charge. Versus many of the polyatomics, they have more than 1 atom. Here's an example. You don't have to draw these, but this is just an example. These are the ones that we created with the styrofoam, and one of them was a sulfate. It has a central sulfur, and it has 4 oxygens surrounding it. And this is going to be the SO4 minus, or the sulfate ion. So multiple atoms, many atoms, but we still have a charge. It's not like a compound. It's still an ion. Transition metals have multiple ion forms, such as iron 2, and again, we have the Roman numeral that indicates the charge right here. So that Roman numeral 2, the Roman numeral is equal to the charge. So for example, if we had Fe3+, this would then be iron 3. Finding the molecular formula using the periodic table, or ionic state, and the crisscross method. Okay, so I'm going to do some setup information here for you because we need to determine the formula based upon the periodic table. So if we can create a little periodic table, a sketch of one. Here's going to be your group 1, and here's going to be your group 2 or group 2A. then if you remember, we have these big box of transition metals. Okay, then we have the group 3 over here, going down, etc. Then we have the group 4, group 5, group 6, group 7, and group 8. So group 1 is positive 1, group 2 is plus 2, and group 3 is a 3 plus. Group 4 is typically, for our sake, we've been knowing them as being neutral. Then we get to the negative ions, typically negative 3, negative 2, negative 1, and 0. So there's this trend that we have plus 1, plus 2, plus 3, 0. Negative 3, negative 2, negative 1, 0. All these guys over here on the left-hand side tend to be metals. And on the other side, they tend to be non-metals. So the positives are going to be your metals. The negatives are going to be non-metals. So we have positive metals. We have negative non-metals. Okay, actually, excluding the group 4 and group 8, because these are going to be your noble gases, and of course these won't be charged at all. So we should probably say here, these guys don't have any charge. Group 4 typically don't have charges. The lower ones do, but we're not going to be including those as part of our information. Okay, but also how do we do this versus the crisscross method? We'll be getting to that when we get to a couple more examples. Determine the charge and names of binary ionic compounds such as magnesium chloride, MgCl2. So binary ionic compounds, meaning that I have bi means 2, so I have 2 elements, magnesium and chlorine. Because I have 2 elements, I have a monoatomic ion and a second monoatomic ion. So I have 2 monoatomic ions. So a binary ionic compound is composed up of 2 monoatomic ions. The way that you name this is it gets the full metal name. So it's the full metal name. And the nonmetal ends in IDE. The nonmetal ends in IDE. Okay, so let's go ahead and do a couple examples. The first one that we're going to be taking a look at is going to be FeCl3. Okay, from this, I need to name this. The first one gets the full metal name, but you have to recall that this is a transition metal. So if it's a transition metal, we're going to need a Roman numeral. How do we determine the Roman numeral? We can do the crisscross, or in this case, we'll be doing the reverse crisscross. This tells me that there's going to be a charge of 3 plus. There's 1 Fe, so the chlorine is going to have a charge of a negative. So the name of this is going to be iron 3 chloride. Let's try another one, and it's we're going to go to the name. So we're going to start with the name, and we're going to come up with the formula. So if I give you calcium oxide, are you able to get the formula for this? Go ahead and pause and see if you can come up with the formula. So hopefully you've come back, and we need to list the symbol for the calcium, which is going to be a Ca. The symbol for the oxygen or oxide is oxygen, CaO. If you look on the periodic table, the charge of the calcium is a 2+ because it's a group 2. Oxygen is a group 6, so it's going to be a 2-. So oxygen would be in this group right here. Now, do I need to crisscross these? And the example, or the answer is no. We don't need to crisscross because they have the same charge. They balance each other. So no crisscross in this case. So the final formula would simply be CaO. How about iron 3 oxide? Iron 3 oxide. Can you come up with the formula for this? Okay, hopefully you tried that. And we need to list the Fe, and the Roman numeral tells me this is a charge of 3+. If I go to the oxygen on the periodic table has a charge of 2-. And if I do the crisscross, I will get Fe2O3. So this is how we do these, particularly with transition metals, those that are not transition metals, those with different charges with the crisscross or reverse crisscross, and those with the same charge, which means that we're not going to crisscross. Determine the charge and names of ternary compounds with polyatomic ions. So again, ternary compounds mean that we have 3 or more elements in our compound. 3 or more elements. Notice how you have sodium, carbon, oxygen. 1, 2, 3. Okay, this is going to be a ternary compound. Okay, we also see that Na is a metal, so we know that's going to be a ternary ionic compound as well. We have a metal and a nonmetal. In this case, we have a metal and we have a polyatomic ion. So this is going to be a mono. The sodium is the monoatomic ion, and the CO3, because we have more than 2, this is going to be the polyatomic. So while binary compounds are formed of 2 monoatomics, a polyatomic has 2 or more elements in the ion. Two or more elements in the ion. So we have a monoatomic and a polyatomic. That's going to create a ternary compound. In this case, it's going to get the full metal name. And also, you'll refer to the polyatomic chart. You'll look up CO3. It will tell you the name is carbonate. So you'll refer to the polyatomic chart for this. So the name for this compound is going to be sodium for the Na and carbonate for the CO3. This you can find on the periodic table. This you can also find on the table that I have given to you guys. It will also be posted on the final as well. Okay, so let's go ahead and do a couple of these. Let's say that we have aluminum sulfate. So we have aluminum sulfate. Can we come up with a formula for this? Please try to do this right now using the information that you have. Okay, so the charge of aluminum is Al, and it is 3+. going to the polyatomic chart, we find the sulfate, which is SO4. It's going to be 2 minus. So we have to do the crisscross for this. And what we find here is that the 2 will come over here for the Al, so I have 2 Als. And then I have, how many SO4s do I have? I have 3 of them. SO4, and I have 3. But I can't just leave it like this, so I have to use parentheses to protect that sulfate to show that I have 3 of those sulfates. So that's going to be the formula for aluminum sulfate. Well, what's the name of this one? We have CuCN2. Okay, so if I look at my periodic table, my Cu is going to be copper. But then you have to ask yourself, is copper a group 1, a group 2, a group 3, or is it a transition metal? And the answer is it's a transition metal because it's in that middle block. So I have to do the reverse crisscross to find out what copper it is. And this would tell me that it's a copper 2+. So that means I have to have a copper 2 there. Cn is a polyatomic ion, so I go to the polyatomic chart, and it tells me the name is cyanide. So we went from the name to the formula, and from the formula to the name. One of them was a regular metal, group 1, 2, and 3. One of them was a transition metal. If it's a transition metal, you need to make sure that you have a Roman numeral. So your ionic compounds can be binary, such as magnesium chloride, or they can be ternary, like this, sodium carbonate, aluminum sulfate, or these that we just did over here. Now we're going to look at binary molecular compounds. Bi, again, means 2. However, molecular compounds do not have ions. Binary molecular compounds are covalently bound. So it's 2 nonmetals that are covalently bound. What this means is that there is no ions here. Okay, you probably know this. How do I name this? This is very similar to a gas that's produced from your automobile. It is actually produced by the automobile, but not in the large amounts that the other one is. This is carbon monoxide. So we have carbon monoxide. So mono, meaning 1, we're going to have to use the prefixes. So we're going to be using prefixes for our naming. So the prefix chart, the prefix chart will be on the test for you. And remember, this gets the first, is going to be the first full name of the element. The second one ends in "ide." And we never use mono if it's just for the first one. No mono for the first. So we don't say monocarbon monoxide. You don't say monocarbon dioxide. Okay, so can you give me the name for this? C3P4. Okay, go ahead and try to name that now. Okay, so we have to use prefixes. So we're going to have a tri, 3 meaning tri. First one gets the full name, tricarbon. 4 is tetra. The second one ends in IDE, so this is a phosphorus. So this is going to be tetraphosphide. Tri for the 3, carbon for the C. 4 is tetra, and for the phosphorus, ending in IDE. Can you also do this? We have pentaphosphorus. dichloride. Okay, see if you can come up with the formula for this. Okay, penta is 5, phosphorus is the element. So P is the element, P5. Chloride is in reference to the chlorine, so I have a chlorine, and di means 2, so it's going to be P5Cl2. Okay, that's the end for chapter 9. We're going to now go through chapters 10, 11, and 12. I'm going to give you some opportunities to work on these problems as well. They're going to be taking a few minutes of your time. And again, I'd like you to pause to try these, and then we'll come back and we'll see if you have the correct answer. So convert from grams to liters or grams to molecules or liters to molecules by first converting to moles. This is mole city. So this is going to be a numerical problem right here. So to remind you, here is mole city right here. And we have liters, and we have grams, and we have particles over here. The particles can be either atoms, they can be compounds, or they could be ions. So I'm just going to list them as particles. The magic number when going to and from between moles and liters is going to be 22.4. When going between moles and particles is going to be 6.02 times 10 to the 23. With grams, we have to calculate what the molar mass is. And that depends upon each individual molecule that you're looking at. Okay, so imagine that you have 50 grams, I'm going to do this one up here, 50 grams of CH4. Question is, how many liters is this going to be? How many liters will you have? So we're going from grams and we're going to liters, which means we first need to use the molar mass, and we also need to use 22.4. So I'd like you to calculate the molar mass of this, use it as a ratio here. We're going to have it, this is going to be a two-step problem, going from grams to moles and then from moles to liters. So it's a two-step problem. What I'd like you to do is to calculate the molar mass over here by adding the sum of the atomic masses, and we'll see what you guys get. So please pause the video and come back when you're done. Okay, so first I have grams, and I have to convert from grams to moles. 1 mole of CH4 weighs how many grams? Well, this is what we have to calculate. So over here I'm going to have a separate problem. My CH4 has 1 carbon, I have hydrogens, and I have 4. The mass of each carbon is 12.0. The mass of each hydrogen is 1.0. Therefore, the total mass of carbons is going to be 12.0. The total mass of hydrogens is going to be 4.0 because I have 4 times 1. When I add these together, the mass of the entire compound will be 16. So 1 mole of CH4 weighs 16.0 grams. So the grams cancels. I'm now in moles. Now I want to convert to liters. Converting from moles to liters. 1 mole of CH4, it's a gas, is going to have what volume? And it's 22.4. So what you do is you multiply everything on the top, this times this times this, but you're multiplying by 1, so it's really this times this, and divide everything on the bottom. Well, it's 16 times 1, but the 16 times 1 will not change the value, so it's this times this divided by this, and it should give you 70 liters of CH4. Now let's go a different route. Let's say you have 50 grams of CH4. we want to figure out how many molecules of this do I have. So how many molecules? So I'm going from here to here. And I'm going to moles first, so I have to use the molar mass. Then I'm at moles, then I have to use Avogadro's number, 6.02 times 10 to the 23rd. So I have the need to, here's my grams, I need to cancel my grams and convert it to moles. Well, we already did this problem earlier where we have the molar mass. So 1 mole of this substance weighs 16.0 grams. Now I need to convert from moles to particles. Canceling units will go on the bottom of moles, and molecules will go on top. 1 mole has how many molecules? 1 mole has 6.02 times 10 to the 23rd. So it's going to be this times this divided by this. Now, let's see. How many moles will I have approximately? 1 mole is 16. I actually have 50. This actually is about 3 moles of material, which means I'm going to have 3 times this, which is going to give me something to the 24th power, because 3 times 6 will be 18. So it's like 18 to the 23rd power, and on your calculator, though, it's going to come out to be 1.8 times 10 to the 24. That's going to give me an approximation. On your calculator, if you do the mathematics, you should come up with this, and please use your calculator and do this and test it. You should come up with 1.9 times 10 to the 24. Now, if you have scientific notation, it's in the denominator, you have to make sure that you're using parentheses. Because remember, if you have multiple things that you're multiplying, like if this problem we're saying I have this many molecules, how many moles do I have? You'd have to actually divide by this number. And when you divide, you have to make sure that you use parentheses. If you're unsure, just put everything in parentheses when you're multiplying, and that will safeguard that you get the right answer. Calculate the percent composition by using the percent of each molecule by mass in grams. So we're going to have the molecule of hydrogen peroxide, which is H2O2. So percent composition, if you remember, percent means part of a whole. So we want to find out what is the percentage of hydrogen in this whole thing, what is the percentage of oxygen in the whole thing. So the first thing that you have to do is calculate what's the molar mass of the whole thing. So it's, again, it's parts per whole. So I'm going to list my hydrogens and my oxygens, and I have 2 of each. Each hydrogen weighs 1.0. Each oxygen weighs 16.0. Can you get, first of all, what the molar mass is of H2O2? Two times 1 will give me 2.0. 2 times 16 will give me 32.0. That means H2O2, the whole thing, weighs 34.0 grams. Okay, so this is the whole, and each of these are the parts. So it's going to be the part divided by the whole, and the part divided by the whole. Okay, so for example, for hydrogen, you're going to take the part, which is going to be 2.0. The hydrogen weighs 2 grams. What does the whole thing weigh? It weighs 34.0 grams. And I multiply this by 100. And if you do that on your calculator, you'll get to 5.9%. Will you please do the same thing for the oxygen and to see what the percent composition of oxygen is? Please go ahead and do that now. Okay, so for the oxygen, oxygen weighs 32 because we have 2 of the oxygens. The whole compound weighs 34.0 grams. And again, I multiply this by 100, and this gives me 94.1%. Both of those percentages should up to be 100%. So that's chapter 10, using molecity and percent composition. Okay, so this will be our last concept here. We're getting through chapter 11. And I'm going to put a reaction over here, and it's going to be 2H2O2 produces 2H2O plus O2. Hydrogen peroxide will fall apart into water and oxygen. Okay, we have products, reactants, coefficients, and subscripts. Which of these are the products? Okay, over here, these will be my products. It's what's being produced. Over here, this actually will say is my reactant or reactants. Your starting stuff are your reactants. The ending stuff are your products. Which are the coefficients? So this is a purely concept. This is not a mathematical problem. So actually this one is mathematical as well, so should we put that up there? So the subscript is going to be these little numbers down below. The coefficients are going to be the number that is in front. And again, the coefficient tells you the number of those compounds, number of the compounds, and the subscript tells you the number of atoms of that element. So the coefficient tells you how many of those particles that you have. This tells you the number of atoms of elements of that element that you have. These are the classic 5 reactions. Okay. We have a combination. Remember, a combination is when you are combining 2 things and they become 1. Decomposition is when you take something, one thing, and it falls apart into 2. Single replacement is when you have usually an element as a reactant. You have an element as a reactant. For example, if you have zinc plus hydrochloric acid, this is what I use to create hydrogen gas to blow up the Pringles can. Okay, this creates, we need 2 of the hydrochloric acid. This will create H2 plus ZnCl2. So we're starting off with a single element right here. Here's the zinc. And it's going to replace the H in the HCl. So then I get ZnCl over here, but ZnCl2. And it kicks out the H to create hydrogen gas. Double replacement, I have 2 ionic compounds. I have 2 ionic compounds. So for this I have, for example, CaCl2, calcium chloride, and Na2CO3, sodium carbonate. What happens is the calcium is going to switch places with the sodium. So notice how I don't have a single element like I have right here for the single replacement. Double replacement requires 2 ionic compounds. And when these switch places, the calcium kicks out the sodium, and I will get CaCO3. The Na kicks out the Cl, and I get 2 NaCls. These would probably be matching types of problems like it was on the previous test. Can you identify which is which reaction? And combustion. Combustion requires O2 as a reactant. O2 is a reactant. So, for example, if we're taking our methane, which is from the pipes in our room, and you add oxygen, this will create carbon dioxide and H2O. We're burning the methane in the presence of oxygen. That's it for the review. Please let me know if you have any questions via email, and we could do a Zoom chat if you need to.